I have already discussed the polarization factor, atomic scattering factor and crystal structure factor, which affect the intensities of the diffracted lines in the pattern taken by a Devasherar camera. Now, I will talk about another important factor known as the Lorentz factor. The Lorentz factor is actually a combination of three geometrical factors, and these factors are based on the following facts. Number 1, intensity of a diffracted beam is also appreciable at angles deviating slightly from the exact Bragg angle. So, this is quite important. The second fact is the integrated intensity for diffraction at any particular Bragg angle will depend on the number of crystallites oriented at or near that angle. And the third fact is we always compare the integrated intensity per unit length of a diffraction line with that of another. Based on these facts, three geometrical factors can be considered which will constitute the Lorentz factor. Now, under ideal Bragg condition, when the X-rays are incident at the correct Bragg angle with respect to atomic planes within a sample, we expect to get a diffracted beam of X-rays making an angle 2 theta b with respect to the incident X radiation. However, what we find in practice is that if we plot intensity versus 2 theta b at the correct Bragg position, we get not only a high enough intensity, but there is some intensity available even for angles other than the Bragg angle on both sides. So, this indicates that there is some diffracted intensity even when we are slightly deviating from the exact Bragg condition, as a result of which the intensity versus 2 theta b plot does not show a straight line only at the correct 2 theta b, but the line profile shows a shape of this type. Now, let us suppose that we are having a non-ideal Bragg condition. Say for example, if this is the incident angle for the X radiation and if this is the diffracted rays, that this is the 2 theta b, we can have a situation where the incident angle is not exactly theta b, but slightly less or slightly higher than theta b. So, these two conditions are given by this line and this line. So, the incident radiation, if it is falling on the crystal surface at angles slightly lower or slightly higher than theta b, the Bragg angle, what situation will arise. We will now examine that. Now, here the delta theta, the deviation from the exact Bragg angle, has been shown on a very, very magnified scale. You see, in order to understand this clearly. Now, the situation is, even when the angle of incidence is slightly lower or slightly higher than the exact Bragg angle, then also in the original direction of diffracted X-rays, we will have some contribution due to the incoming X-rays. That means, if the height from the base to this point is due to diffraction under ideal condition at 2 theta b position, there will be some extra intensity also due to the non-ideal condition of diffraction. So, we say that the maximum intensity which we get during diffraction will be mostly composed of the diffracted intensity under ideal Bragg condition plus a little bit extra due to diffracted intensity from non-ideal condition. If we go back to the previous figure, we see that the diffraction profile has got a shape like this. So, this is the maximum intensity. Now, if we come down to an intensity level which is half of I max, the breadth of the diffraction profile B is a very important parameter. So, if we want to find out the total intensity of diffraction from a set of atomic planes, we have to consider the whole intensity not only at the 2 theta b position, but also at the other positions. You see, when the exact Bragg law is satisfied, we get the maximum intensity of the diffracted beam. This is due to the fact there is 100% constructive interference of the rays scattered by the different atoms. But even when there is not 100% constructive interference, then also we will get some intensity. That intensity will be much lower than when there is 100% constructive interference, and that is the reason why we get a line profile of this shape. And the total intensity of diffraction for this particular line will be proportional to the area of this line profile, or in other words, it will be proportional to I max multiplied by B. And as I have already told you that under non-ideal Bragg condition, there will be some intensity, extra intensity, which will also be there at the 2 theta b position. So, this much of intensity is due to the situation where exact Bragg law is satisfied, and this extra comes from the fact that even when the Bragg condition is not fully satisfied, there is a slight deviation of the incident angle from the Bragg angle, then also some intensity will appear at 2 theta b. Now, you see that this intensity at 2 theta b will depend on the value of delta theta. If you can have a larger value of delta theta when some intensity is still possible to have in 2 theta b position, then you will get an extra intensity in the diffracted beam. So, the intensity of the diffracted beam, or rather the I max, will be proportional to the value of delta theta. So, this can be written as I max will be proportional to the value of delta theta, and it can be shown that this is proportional to 1 upon sine 2 theta b. That is proportional to 1 upon, I am sorry, it is proportional to 1 upon sine theta b. It is proportional to 1 upon sine theta b. So, we see that due to non-ideal condition of diffraction, I max, which is proportional to delta theta, will be proportional to 1 upon sine theta b. This I am saying without any proof. Now, if we look at the breadth of the line profile b, then also it can be shown that this is proportional to 1 upon cosine theta b. So, you say that delta, the I max is proportional to 1 by sine theta b. I have shown it without any proof. Similarly, it can also be shown that b, the breadth of the line profile, is proportional to 1 upon cosine theta b. Now, the integrated intensity, which will be proportional to I max into b, will be proportional to 1 upon sine theta b cosine theta b. So, this will be proportional to 1 upon sine theta b, 1 upon cosine theta b. That means, it will be proportional to 1 upon sine 2 theta b. So, we realize that the integrated intensity of a diffraction line, which is proportional to the maximum intensity available at 2 theta b and the breadth of the line at half maximum intensity, is also proportional to 1 upon sine 2 theta b. So, this is the first geometrical factor that comes into the Lorentz factor. Now, let us talk about the second geometrical factor, which is also part of the Lorentz factor. Say for example, if we have a sample here and this shows an atomic plane which is poised for diffraction. This is the incident beam, which is incident an angle of theta b, the Bragg angle, and so this is the diffracted beam of X-rays, this is 2 theta b. Now, we normally assume that all the crystallites arranged in a powder sample, they are arranged in a very random fashion. Therefore, the number of crystallites which will give rise to diffraction from a particular atomic plane will be the same as the number of crystallites, which diffract crystallites which will be diffracting from a another particular plane, etc., etc. That means, since the arrangement, since there are the total number of crystallites in a powder sample, they are arranged in a random fashion. Therefore, it is sometimes it is very natural to assume that we will have a similar number of crystallites which will give rise to all the different diffracted beams from the different planes. That means, if you have a plane H1, K1, L1, if you have a set of planes H1, K1, L1, then H2, K2, L2 and say H3, K3, L3. So, since all the crystallites in the polycrystalline sample in a Debye camera, they are randomly arranged, it will be quite natural to assume that the number of crystallites within this sample which give rise to diffraction from this plane will be the same as the number of crystallites which give rise to diffraction from this type of planes will be equal to the number of crystallites which give rise to diffraction from this type of planes. But this is not actually true, as we will see right now. Say for example, in this particular case ON is the normal to the HKL plane shown here. ON is the normal to the HKL plane shown here. We know that even when non-ideal Bragg condition is fulfilled, there will be some diffraction. That means, we can find out that even when the perpendicular to the HKL plane is not ON, but slightly deviated from this, say by an angle delta theta, then also we will have diffraction in the 2 theta b direction. So, these two lines, they will specify a ribbon like element within a sphere which we draw with O as the center. So, we can say that all the crystallites that will be available to diffract from this particular HKL planes, their plane normals, they will appear within this ribbon element, So, the total number of crystallites which are available for diffraction from this particular atomic plane, the number will be proportional to the area of this ribbon like element. And if we consider the total number of crystallites in the sample at O, then the total number of crystallites, the number will be proportional to the area of the entire sphere. So, you see that this ribbon like element, the area of this ribbon like element will vary depending on the HKL plane. So, that is the reason why, even though we have the crystallites arranged in a very random fashion in the polycrystalline sample, the number of crystallites which will give rise to diffraction from a particular plane will vary from plane to plane. So, in this particular case, diffraction will occur from a number of crystallites whose number is proportional to the area given by this ribbon element. So, what is the fraction of crystallites that we will get? What is the fraction of crystallites that will diffract radiation from this particular plane? You see, if you look at the ribbon like element here, this angle is delta theta. So, if the radius of this ribbon like element is small r, r delta theta will be the width of the ribbon. So, r delta theta will be the width of the ribbon. And what is the length of the ribbon? The length of the ribbon will be 2r, 2 pi r sine 90 degree minus theta b. So, you see that this is the width of the ribbon and this is the length of the ribbon. This is the width of the ribbon and this is the length of the ribbon. So, the total area of the ribbon is given by r delta theta multiplied by 2 pi r sine 90 degree minus theta b. So, the total number of crystallites in the polycrystalline sample which will give rise to diffraction from this particular atomic plane HKL plane will be proportional to this value, and the total number of crystallites in the sample itself, they will be, the number will be proportional to the area of the entire sphere centered at the point O, and we know that that area is 4 pi r square. So, this is nothing but the fraction of crystallites. This is the fraction of crystallites available for diffraction from a particular HKL plane. So, this is a very important thing. You see, normally we assume, we have the idea that since the total number of crystallites in the polycrystalline sample in the Debye-Scherrer method, they are randomly arranged. So, the number of crystallites within the sample which will give rise to diffraction from H1 K1 L1 plane or from H2 K2 L2 plane or from H3 K3 L3 plane, they should be similar, but this is not true, simply because of the fact that the fraction of crystallites available for diffraction from a particular HKL plane, it is different. So, all other factors remaining constant, only because of this fact the intensity of the diffracted beams will vary. Now, so this fraction will be equal to delta theta cosine theta b divided by 2. So, it immediately tells us that I max, the intensity diffracted in this particular direction, will be proportional to cosine theta b. So, I max will be proportional to cosine theta b. So, this is the second geometrical factor which constitutes the Lorentz factor. The first one was that the integrated intensity, the I max into b, is proportional to 1 by sine 2 theta b. The first factor was this. The second factor is the fraction of crystallites available for diffraction from a particular HKL plane. Because it is different, I max will be proportional to cosine theta b. Now, let us talk about the third geometrical factor. You see, when we talk about a diffraction line, say for example, in the Debye-Scherrer method, these three indicate 3 diffraction cones from 3 different diffracting planes. So, these 3 show the 3 diffracting cones of radiation from 3 diffracting planes. Now, the arrangement of the film is such that we do not record the entire intensity that is present over the cone. We measure only a part of it in the only a part of it in the film. Say for example, here, so the total intensity diffracted should be calculated over the entire circular area of the Debye ring. Similarly, for this case also, the entire the total integrated intensity should be considered from this entire Debye ring, but we are not doing that. Actually, we measure the intensity on unit length from each cone, so to say. So, because of the arrangement and the shape of the recording film, we record only a little bit, say unit length of the total length of a diffraction cone in every case. So, you see that because of that, what will happen? The intensity measured from the lines on a Debye-Scherrer pattern, those will be underestimating the total diffraction intensity in this case and will be overestimating the total diffraction intensity in this case. And because of that, we have to have some factor which must be multiplied, which must be used in order to rationalize the intensities from the different diffraction from the different HKL planes. Now, if you look at the size of the cone here, so this angle is 2 theta b. So, naturally, and if this is the r is the radius of the camera, then we can write down that the length of the cone, the base of the cone is 2 pi r into sine 2 theta b. So, the length of the base of the cone in a particular case is equal to, so this is r, this angle is 2 theta b, this length will be 2 pi r sine 2 theta b, where r is the radius of the camera. So, we do not measure the intensity over the entire length of the base of the cone. We measure the intensity from, say, unit length from this cone. So, in fact, our integrated intensity is proportional to 1 upon 2 pi r sine 2 theta b. That means, I is proportional to 1 upon sine 2 theta b. So, this is another important relationship that we get. So, from the first condition we found that I max b, the integrated intensity of a diffraction line, is proportional to 1 upon sine 2 theta b. Then in the second case we find that I max is proportional to cosine theta b, and again over here actually this is the total integrated intensity is proportional to I 1 upon sine 2 theta b. So, if we look at the integrated intensity, if we combine these two factors, so if we combine integrated intensity, if we combine these three geometrical factors, then we find the integrated intensity will be proportional to 1 by sine 2 theta b multiplied by the second one cosine theta b multiplied by the third one 1 by sine 2 theta b. So, this will be proportional to cosine theta b by sine square 2 theta b, or this will be proportional to, if we break it down further, it will be proportional to 1 upon 4 sine square theta cosine theta. It will be 1 upon 4 sine square theta cosine theta. So, we see that because of these three geometrical factors, the integrated intensity will be proportional to, for any line will be proportional to this value 1 by 4 sine square theta cosine theta. Now, if you remember, while we determined the polarization factor, in the polarization factor the integrated intensity was found to be proportional to 1 plus cosine square theta. So, this is what I am sorry cosine square 2 theta. In the in case of the polarization factor, we found out that the integrated intensity is proportional to 1 plus cosine square 2 theta. So, now we can combine this with this, and we can find out, we can say that if we talk about the Lorentz factor as well as the polarization factor, then the Lorentz polarization factor, it says that integrated intensity of a diffraction line will be proportional to 1 plus cosine square 2 theta divided by sine square theta cosine theta. You know, this 4 we have taken out, is a constant. So, you see that the due to the effects of both the polarization factor and the Lorentz factor, the integrated intensity will be proportional to this quantity 1 plus cosine square 2 theta divided by sine square theta cosine theta. Now, 3 other factors are remaining to be discussed, and those are the multiplicity factor, the absorption factor, and the temperature factor. Now, what is the multiplicity factor? You see, every other factor remaining constant, if we find that in a particular system of planes, say 1 0 0, how many 1 0 0 planes are there? There are 6 different types of 1 0 0 planes. Similarly, if we talk about the 1 1 1 planes, there are 1 2 3 4 5 6 7 8 with different indices. So, there are 8 planes are there. So, every other factor remaining constant, when we find out diffraction from the 1 0 0 planes and diffraction from the 1 1 1 planes, then we will see that the ratio of the diffracted intensity should be 6 by 8, only because of the fact that the number of planes in a particular system of planes is not equal. So, all other factors remaining constant, since the 1 0 0 type planes there are 6 of them, and 1 1 1 planes there are 8 of them. So, integrated intensity from the 1 0 0 plane divided by the integrated intensity from the 1 1 1 type of planes will be simply 6 by 8. So, these numbers 6 for 1 0 0 plane, 8 for 1 1 1 planes, these are known as this is known as the multiplicity factor. So, multiplicity factor for 1 0 0 planes is simply 6, and multiplicity factor for 1 1 1 planes is 8. In a similar manner, we can find out the multiplicity factor of the other type of planes, and naturally in the integrated intensity has to be multiplied by the multiplicity factor in every case. Then comes what is known as the absorption factor. Now, if we have a cylindrical specimen like this, if we have a beam of X-rays incident in this fashion, in this direction, and if we consider diffracted intensity at low theta values as well as diffracted intensity at high theta values, what we will observe? We observe that those radiations which are diffracted at low theta value, they have to, the diffracted intensity as well as the incident intensity has to pass through a longer distance within the sample. But when you consider the diffracted intensity at a high theta value, then we find that the distance travelled by the incident radiation and the diffracted radiation, we add up, they have to travel much less through the specimen. So, in case of the low theta value diffraction, we find there will be more of absorption of both the incident and the diffracted beams by the sample, and if we consider diffracted intensity at high theta values, the total absorption of the incident as well as the diffracted radiation by the sample will be much less. So, simply because of absorption, we find that intensity in the high theta of the diffracted beams in high theta region should be more than intensity of diffracted beam at low theta values. All other factors remaining constant, absorption will cause a higher intensity of the diffracted beam at high theta values and at the lower value of the diffracted intensity for lines at low theta values. Then comes the temperature factor on the integrated intensity of a diffracted beam in the Debye-Scherrer method. Now, we consider two different cases. One, very low temperature situation when the atomic planes are very narrow. They can be considered very narrow because at low temperature the vibration of individual atoms on an atomic plane will be very less than in case of a high temperature situation, where because of the higher temperature the amplitude of vibration of an atom from its mean position at the temperature T is say about u. That means, in one case at low temperature the diffraction is taking place from an atomic plane, but in case of diffraction at a higher temperature the atomic plane behaves like a plate-like element. So, it is not a simple plane, but it is a diffuse plane, so to say. Naturally, what will happen, the Bragg condition will be fully satisfied in this case more or less, but the Bragg condition is not going to be fully satisfied in this case, because the plane is no longer a plane in the ordinary sense. Now, the plane is more or less diffuse with some amount of thickness attached to it. Now, when such a situation arises, in general the integrated intensity will be much lower in this case than over here, but the effect of temperature on the integrated intensity is not the same for lines diffracted in the low theta region and the lines diffracted in the high theta region. Say for example, if u divided by d, d is the interplanar distance of the plane that I am considering here, is very high, then what will happen? The degree of constructive interference will be low. As a result, there will be lower integrated intensity in this particular case. On the other hand, if the ratio u by d is low, that will mean high degree of constructive interference of the diffracted rays, which will mean higher integrated intensity. But how u by d can be high if d is low, and how u by d can be low if d is high. Now, a low d means we are talking about lines which are getting diffracted at higher theta values, because lambda is equal to 2d sin theta. So, if d is low, theta will be high. Similarly, high d means low theta values. So, what we find? We will find that those lines which appear at higher values of theta, they will be having lower integrated intensity, and those lines which are diffracted at lower theta values, they will have higher integrated intensity due to the temperature factor. Now, when we talked about the absorption factor, we found completely the opposite situation. There we found that absorption will be much higher in the low theta direction. So, as a result, integrated intensity will be lower here. So, integrated intensity will be lower in this particular case, and on this side, on the high theta region, absorption is less. So, integrated intensity is higher. So, this is due to the absorption in the specimen, and this is due to the temperature factor. So, due to absorption, high theta lines, their intensity will be higher, low theta lines, their intensity will be lower, and due to high temperature, high theta lines will have lower intensity, and low theta lines will have higher intensity. So, we see that the effect of absorption is the reverse of the effect of temperature, and since it is very difficult to calculate the exact effect of absorption as well as temperature so far as the integrated intensity is concerned, we assume that the effect of one nullifies the other. So, when we determine the integrated intensity from a diffraction line, we do not consider absorption factor and the temperature factor at all. So, now for a Debye-Scherrer method, the integrated intensity or the relative integrated intensity can be written by this expression, where f square, this is the square of the crystal structure factor. We know that crystal structure factor is an amplitude, so square of that is the intensity. So, that is why this will appear in the intensity equation as f square. P is a multiplicity factor. So, if for a particular plane multiplicity is higher, then it will show a higher intensity. If for a diffraction line for which the multiplicity factor is lower, will show a lower intensity. And what about the 1 plus cosine square 2 theta divided by sine square theta cosine theta? This is the Lorentz polarization factor. Now, we have left out the temperature factor and the absorption factor from the intensity equation, because as I already mentioned, the effect of the other is exactly the opposite of the effect of one is exactly the opposite of the effect of the other. Therefore, we can say that if we want to find out the relative intensity of a diffraction line in the Debye-Scherrer method, it can be given by an equation of this type. Now, things are complicated in case of the relative intensity of diffraction lines as we find for in case of a diffractometer. So, here the expression is I, the integrated intensity or rather relative integrated intensity, is equal to I0 e to the power 4 lambda cube A m square divided by m square C4 into 32 pi r whole thing by 1 by v square and f square p 1 plus cosine square 2 theta sine square cosine theta e to the power minus 2 m and 2 mu. Now, I is the integrated intensity of a diffraction line, I 0 is the intensity of the incident X-rays, E and m are the charge and mass of an electron, c the velocity of light, lambda is the wavelength of the incident radiation, small r is the radius of the diffractometer circle, A is the cross sectional area of the incident beam, small v is the volume of the unit cell of the reference material we are examining, F is the crystal structure factor, P the multiplicity factor, theta the Bragg angle, and 1 plus cosine square 2 theta by sine square theta cosine theta is the Lorentz polarization factor. This factor e to the minus 2 m, we have not explicitly written what it is all about, is a temperature factor, and 1 by 2 mu is the absorption factor, where mu is nothing but the linear absorption coefficient. So, you see that depending on which kind of method we are using, it is possible to find out the relative integrated intensity of all the diffraction lines that appear in the pattern of the material.